I manage a portfolio of programs in thermal management. Prior to coming to DARPA, I had an academic position at Georgia Tech. And of course, as far as what keeps me awake at DARPA are keeping things at controlled temperatures and removing heat. And in fact, the problem that was articulated earlier by my colleague Dan Ridge of keeping these rusty razor blades at fixed temperatures, that's the type of things that I worry about. But today, I'm here to talk to you about cryogenic cooling, which I believe holds the key for next generation high-performance computing, as well as a whole array of other microsystem applications. Let's take a trip down the supercomputing memory lane. This is about, that grainy picture on the left is about 35 years old, and it dates back to this supercomputing race at the time, where Seymour Cray had gone on and formed his own company, and CDC, which is where Cray, I believe, was previously, decided to start its own supercomputing division, a spin-off called ETA, and they came up with this ETA-10 supercomputer, and you can kind of see a picture of that. It had 4 processors at the time, so each of those 2 cabinets in the foreground house 2 CPUs that are cryogenically cooled at liquid nitrogen temperatures. And further back in the data center, you can see some of the memory hardware. With that, they were able to show a 10x improvement with the CMOS capabilities at the time, achieving something on the order of 10 gigaflops of performance, which was at the time considered to be great. And there were 6 of these machines made. I think the first one was deployed at Florida State University. And there was an air-cooled version, 15 of those were made as well. But within 3 years of launching this effort, it all ran into financial difficulties, and all of these were closed down. And the final set of machines were actually offered to high schools. I think one of them was Jefferson Science School, which is in our neighborhood in Alexandria, Virginia. So, of course, that showed that certainly it wasn't something that was economically viable then. So let's take a look at what has happened since. DARPA has had a program called LTLT, and we have demonstrated significant success in terms of performance per watt. So if I take a look at some of the information that's on the right, on the lower right, you can see that by looking at bespoke transistors that are designed for optimal operation at liquid nitrogen temperatures, you can get a significant improvement in speed up. With that, let's try to do sort of a calculation for a small to medium-sized data center today, maybe a 5 megawatt data center. And let's look at what that would mean. And again, this is sort of a very simplified calculation. You could poke holes through it, possibly drive a truck through it as well. But I think it's sort of illustrative of where the state of the art is in terms of system-level cryogenic operation. And if you look at maybe much more reduced heat footprint of maybe only about 111 kilowatt, and if you say, well, I'm going to use liquid nitrogen, I'll boil it off, and that's how I'll remove that 111 kilowatt. Well, if you look at the operating cost, this is not the infrastructure cost, just the operating cost of that, and compare it with a conventional data center of today, they kind of come out and it's kind of a wash. So that sort of is an indication of why system-level cryogenic operation is a major challenge. And that's where we're interested in seeing what can we do about that. So, of course, that's for conventional CMOS operated at cryogenic temperatures. What about quantum computing? Lots of interest in that, and DARPA is very, very interested in that, as are many other entities. So again, there are so many different types of qubits, and many of you are much more adept in looking at those than I am. But some of these that are superconducting qubits require coming down to temperatures that are on the order of maybe 10 millikelvin. And the only way to get down to those types of temperatures is a dilution refrigerator type concept, which has these different chandelier plates that start from near room temperature and then kind of progressively get down to the lowest temperatures. Of course, there are, by definition, therefore, heat leaks because you're traversing between different ranges of temperatures. Even if you didn't put any hardware in there would still be parasitic heat losses that you'd have to essentially remove if you wanted to maintain it at these temperatures. And by the time all is said and done, with the current equipment, you can get something on the order of maybe 30 microwatts of cooling at the lowest temperature stage. And then if you sort of try to look at, well, then how do I scale my current qubits to possibly maybe millions, which is what is said is needed in order to show quantum superiority, well, there isn't sort of a very clear road that exists. And that's where I think there is a lot of innovation that is potentially possible in the area of both cryogenic equipment. Maybe there are alternatives to getting down to those temperatures. And in addition, maybe there are different materials and packaging architectures that allow for possible reductions in the heat leak that you'd otherwise encounter. So of course, looking at the temperature scales, the cryogenic temperature range would be, let's say, below minus 150 degrees C. And depending upon where you're operating, you could potentially be looking at high temperature superconductivity type applications or low temperature superconductivity, or even down to 10 millikelvins. And there are different sort of working fluids or working substances that get you down to those periodically low temperatures. And of course, at very, very low temperatures, then you have different types of devices that get you down to, let's say, 10 millikelvin. So that in principle is all fine, but if you start looking at the energetics requirements, and those are just dictated by the second law of thermodynamics, you're talking about a significant increase in the electrical power input needed to get down to those types of temperatures for, let's say, given heat load that you're trying to reject. And by the time you go from near room temperature to these deep cryogenic temperatures around, let's say, 20 millikelvin, there is a million-fold increase in the requirement for electricity in order to get down to those temperatures. And that's the reason why you get about 30 microwatts. So certainly that's a major challenge. And if you look at where the current state of the art is, on the left, you see where state of the art for around liquid nitrogen temperatures in cryogenics is. And you can see it's a busy chart, but basically for liquid nitrogen temperatures, the best solutions are either the Stirling coolers or pulse tube type coolers, which can get you anywhere from maybe 5 to 25% efficiencies of the maximum that's possible, dictated by the laws of thermodynamics or the so-called Carnot efficiency, only 5 to 25%. Well, how about getting to higher values? Can we do significant improvements in hardware that at liquid nitrogen temperatures can get us down there with far lower power consumption? If you look at even lower temperatures, the figure on the right, if you're trying to look at maybe liquid helium temperatures, then again, you're talking about efficiency that are even lower. The thermodynamic limits are lower because of the much lower temperatures, and what has been achieved is even lower, perhaps by an order of magnitude. So there is a significant room in terms of trying to come up with cryogenic hardware that can get you somewhat closer to what thermodynamics allow you to do. And that's where we are certainly interested. Now, of course, in addition, there is, of course, the curse of interconnects. These different temperature stages are needed for doing different things. Maybe the control electronics reside at room temperature, then there are various elements of a microsystem that reside at different lower temperatures. And by necessity, there have to be interconnects between them. And as such, there's going to be heat leaks just because of the interconnects traversing these different temperature regions. And that essentially then will limit how much heating can be produced by the active electronics that is housed in these. And just as a very simple representative calculation, this is just looking at the heat leak through the wiring. And of course, and this is the simplest solution, maybe some sort of a coaxial microwave cable. And if you look at, let's say, taking that length of a cable between two stages of this kind of a cryogenic cooler and looking at how much heat leak you're going to get, those are the numbers that are shown in that bar chart. And those are then have to be compared with what's the cooling capacity that you have available. That's the table at the bottom. And that cooling capacity, of course, progressively decreases as you go from let's say, liquid nitrogen type temperatures down to these tens of millikelvin temperatures. And those different sort of colors in the bar charts represent that you have significant opportunities in terms of materials advances that can reduce this type of a heat leak. And certainly that's an area where significant innovation is still possible. So now, of course, the other thing that along with the interconnects is that they don't necessarily all have to be coax microwave cables, optical interconnects, other types of interconnects that could potentially allow reducing the heat leaks, so more electronics could be placed where it needs to be placed. In terms of equipment, of course, this is sort of the, I would say, sledgehammer solution to that. I mean, this is the large so-called Colossus platform, At Fermi Labs, the size of this outer chamber is about 3.4 meter in diameter, 4.5 meter tall. And it allows for something like the capability that maybe 10 commercial dilution refrigerators would allow. So certainly that's something that's quite remarkable, and a lot of 1,000 readout lines. So dramatic improvement in capabilities. But the question then is, how scalable is this? I mean, the size of it, the cost of it certainly would preclude, sort of, at least from what I can see, preclude large-scale usage of it in various types of supercomputing facilities. So are there other architectures? Are there opportunities to sort of combine multiple smaller hardware that could get down to these temperatures? How would that operate? And what sort of efficiencies and capabilities might you get from that? So certainly interest in that. There is also, of course, quite a bit of an active work that is going on in terms of cryogenic, including improving the capabilities of cryogenic refrigeration. On the right is something that is multiple decades of effort that shows sort of incremental advances necessitated by usage required for various types of sensors. And this, for example, is a hybrid design that uses Stirling cooler as the upper stage and a pulse tube cooler as the lower stage, and has shown significant improvement in size, weight, and power. And certainly these are the types of advances. These are necessitated and are somewhat, in my view, incremental. On the left, you see using solid-state optical or laser cooling. In this case, they were able to get down to 135 Kelvin through this laser cooling of the crystal, which is then in sort of conductive contact with the sensor. So again, for a sensor cooling type application in space, aerospace type applications. Can these types of concepts be used at much lower temperatures? Can these improvements be made? Can it be made much smaller? Can it provide significant improvements in cooling power capabilities? All of these are open questions and very, very important in terms of possible deployment as future microsystems. So I'm back to my earlier slide here again, and I see there are significant sort of opportunities that exist in both cryogenic hardware and cryogenic interconnects that would allow for us to move to the next generation in terms of high-performance supercomputers and other types of microsystems. So I invite you to sort of join me in looking at the next revolution in cryogenic packaging and cryogenic hardware development. Thank you.